This is IAQ Radio, Indoor Air Quality Radio, the voice of the indoor air quality industry, with your hosts, Radio Joe Hughes and the Z-Man, Cliff Zlotnick. And now, Radio Joe Hughes.
Good day and welcome to IAQ Radio Plus. Today is episode number 566. We welcome concrete guru Robert Higgins, Bob Higgins. Looking forward to a great show talking about concrete issues and answers. Before we get started, let's thank our platinum sponsor.
IAQ Radio Platinum sponsor is John Don Products, where restoration and abatement contractors shop. Visit them at jondon.com. That's JONDON.com.
I also want to thank our gold sponsors, Particles Plus, Healthy Indoors Magazine, Gray Wolf Sensing Solutions, and AEML Inc. Laboratory. And of course, our association sponsors, CIRI, the Cleaning Industry Research Institute, the Indoor Air Quality Association, and the Restoration Industry Association.
And now you can win a cool prize. It's time for the IAQ Radio Trivia question. Be the first to correctly answer. Simply email your answer to czlotnick@cs.com. Or if listening live, just text your answer from your computer. And now, here's the Z-Man with this week's IAQ Radio Trivia question.
Hello, everyone. Congratulations go out to Doug Conan, Aerotech Environmental, Dayton, Ohio, who was first to identify the term electrical impedance as the measure of the opposition that an electrical circuit presents to a current when voltage is applied. The IQ trivia question for today, Friday, December 6, 2019, has been sponsored by Ideas, a solution chemistry company providing unique solutions to odor removal, surface cleaning, and decontamination problems. Here's today's IAQ trivia question. How much concrete was used in China between 2011 and 2013? Back to you, Joe.
That's an interesting one there, Cliff. Well done. Today's guest, Robert Bob Higgins, has been involved with moisture-related issues in concrete and waterproofing since 1976. And he's been developing products for such use since 1980. He was the product development chemist for SINAK. He's equally involved in product and process development, having developed most of the products manufactured and marketed by that former company, SINAK, as well as owning or co-owning patents for moisture testing. He has expertise in moisture-related concrete issues, having been involved in waterproofing, technical committees, professional groups, lecturing, teaching, and construction defect litigation. Welcome to the show, Bob.
Thank you.
Great to have you here. I thought I knew a little bit about concrete, and then we started kind of getting emails back and forth, and I realized I don't know a whole heck of a lot, Bob, so I'm looking forward to learning more from you today. I think one of the things that really got me thinking about the topic was when you wrote a little something on the history of concrete, and I wonder if you could maybe talk to listeners a little bit about the history of concrete.
Sure. With the history of concrete, I used to recycle the information that everybody else did, that concrete was thousands and thousands of years old, and that's true. However, the type of concrete that was used thousands of years ago has little resemblance to the concrete we use today. Portland cement was basically developed in England, and it was patented, and it's been used since 1824. But we still can't use that information as being a tangible history lesson for what we're using today, because concrete has changed too much. One of the most dramatic changes we've experienced, I learned from a gentleman by the name of Eb Monroe, who wrote an excellent article on this in Concrete magazine, and it was an AIA publication. It was, which covered how they started grinding cement finer back in the mid-50s. When they started grinding it finer, they got better in increased strengths. So rather than continue along that path, what they did is they started targeting the 3,000 PSI at 30 days target, so they actually started backing off on the cement. So if you could magically go back in time and take concrete that's 30 days old at 3,000 pounds and compare the permeability of that to concrete today at 3,000 psi, the relative permeability of that concrete is 75% lower. So we're actually so when people say concrete hasn't changed, that's only true in regards to the chemistry, not in the application of it. So we've actually created worse concrete since the 1950s. And back then, they used to design bridges that could predictably last between 100 to 150 years. Today, they've changed the narrative to where now they're targeting 50 to 70 years. Now, most concrete bridges today, exposed to the same thing these older bridges were, are now requiring repair in less than 20 years. So things have dramatically changed, but people have not been told that. They keep told the same garbage over and over again about the history of concrete. And that's not true, because the old cements that they used were called geopolymers, and it has very little resemblance to Portland cement. One of the best examples is it showed this structure that's still in the Mediterranean. It's not fully intact, but there's pieces left, and it's been soaking in salt water for over 1,000 years. Today's concrete would have disintegrated within decades. We're going to strengthen the concrete rather than weakened it.
So let me see if I understand what you're saying. The Portland cement is still the same. It's just the additives or the way they mix it. Is that accurate, or am I kind of shortcutting it, I guess?
Well, actually, they're just putting less cement in than they used
to. Okay.
So what they did is it's like coffee. If you grind coffee finer, you don't need as much because you get a stronger brew. Cement's much the same way. So when they started grinding it finer, they got increased strengths very early on. So what they did is they just started using less cement. By using less cement, it made a more permeable and more porous concrete. The strengths are the same, but the values of the concrete's durability aren't the same.
Interesting. And that's all cost, I would imagine. The reason they do that is because it costs less.
Yes.
Okay. Very interesting. You know, Cliff had a great question here. Is concrete in your DNA, or is it something that piqued your interest at some point? 1976, let's see, I was 1 year out of high school, and that's when you started in the concrete world. Yeah,
in fact, when my first introduction to concrete sealers, my dad said, "Oh, I found this great concrete sealer." And this back in '76. I said, "Why do you want to seal concrete?" I knew nothing about it. But when I started doing some research on silicates and different treatments they had back then for concrete, I always had an interest in inorganic chemistry in high school. I loved the moon rocks and everything involved crystallization. So that piqued my interest. And I thought, oh, this has really a lot of potential. And as I kept going further and further into it, I realized that there were a lot of misconceptions about how these materials would work and the balancing of them. So the waterproofing, we started developing quite a reputation. So I started getting involved with some projects that were considered nearly impossible to repair, and we would repair them. So I developed a reputation from there.
Interesting. Cliff, let me turn it over to you.
Well, let's see. You mentioned Geopolymer. Can you just go back and explain what a Geopolymer is, Bob?
A geopolymer is simply a mixture of materials that forms an amorphous cement. And that's the way you can spot if something's naturally developed or isn't naturally developed. Naturally developed polymers are typically crystalline in nature because it's heat and pressure that forms those. Whereas a polymer that's created tends to make more of an amorphous cement. And it eventually develops strength, and most of them are alkaline in nature. So, but the difference of the alkalinity can really change the overall durability, long-term durability of these materials.
You use the term amorphous. Can you tell the listeners what that means?
Oh, well, actually, I was doing some work. This was back in the late 80s. I was doing some work with the Army Corps of Engineers. I was down in Vicksburg, and we were dealing with some of that was called ASR, or alkali silica reaction. And that is most active with amorphous materials because they're not as they're not as chemically stable. They're easier to dissolve with alkaline water. And I'm trying to say this as simply as possible so I don't get into all the chemistry. So here's a piece that I took from there. And if you look, I would use this in inspection courses. And if you look at the aggregate, they're nice and smooth, and most of them are round. Most of them are not crystalline.
Right.
And this piece of concrete, when the ASR started, this piece of concrete started out at 10 feet long and ended up becoming 12 feet long. That's how much it expanded from the alkali silica reaction.
So
it expanded 2 feet. So it would cave in walls and disrupt machinery. It causes all kinds of problems.
Jeez. And that's not with freezing. That's just with water.
That's just water. Yes, it's not freezing.
Interesting. And can you give us some examples of other geopolymers that are used in the concrete world? Is that
they're considered specialty cements because without getting too controversial, the Portland Cement Association basically dictates what's acceptable, and they've dictated the rules and regulations for what's considered acceptable for general construction using concrete. So geopolymers are still in the novel category. They're not broadly used. Probably the closest thing that's used in volume compared to Portland cement is probably the calcium aluminate cements, and those again they're really specialty products.
We've had people talk before, and I just want your thoughts on the term curing of concrete and the difference between a concrete that's cured and a concrete that's actually dry, or does concrete ever actually become dry?
Technically speaking, no. Concrete can't become dry, mostly because the alkaline components, such as sodium hydroxide, will begin to pull moisture from the air even if the relative humidity is as low as 8.5%. So it actually pulls moisture. So the air can be dry, but this material will hold some water. And as it's exposed to more water, depending how much alkalinity there is, it will attract more water. So it's disproportionate to the environment. Well, even sand can do that to a certain extent because it's hygroscopic. And that's how soldiers in deserts stay alive, where they're actually able to extract moisture from the air by using sand. They use what's called a solar distillation, and they can actually produce enough water to stay alive.
And then if you could just talk a little bit about the term curing.
Curing is keeping it wet. That's pure and simple what it is. The longer you keep it wet, the longer it cures and the tougher it gets. Concrete's really happy when it stays wet. It's not so happy when it gets dry. In fact, if it dries prematurely, there's a real problem with the cement not fully developing. You want to keep concrete wet for at least 7 days. That's a bare minimum.
7, but that seems like an inherent conflict when we're trying to, build things faster, quicker, less time. How do they manipulate that to try and beat that 7 days, and then what kind of problems can that cause?
Well, there's ways they can beat that, but it's from a general standpoint, it's not very economical. But if time is of the essence, there are specialty concretes. In fact, I worked with one where I helped them develop some things dealing with some moisture tests that were being conducted, where it's called a self-desiccation concrete, where basically there is no free water. The concrete will basically consume all the water that's used in the placement, so there is no free water. So they can actually, in many cases, install a floor in as early as 7 days or 30 days, depending on how it's formulated.
So, what's the in construction? What would be the most common amount of days that they would allow the concrete to cure before they would start to put, floor coverings on, etc.?
Well, that's a tricky question, because it depends on where you are in the country. Some places they want to start installing the floor in 30 days, and some they want to wait a couple of months, and some 6 months. It just depends on the local regulations. Interesting.
And that would be because of the climate that you're in?
Climate, also the pressure on construction schedules, that kind of thing. So
right.
A lot of times I recommend to most clients, I would not exceed a 0.50 water cement ratio. Now, a lot of people don't understand what a water cement ratio is.
Yes, please tell us.
When a 0.50, for example, that means there's half a pound of water for every pound of cement. You judge it based on the weight of water, because water is incompressible. Cement's all over the place. It can change in volume, and you can't really go by its weight. You have to go strictly by the weight of water. So the lower the number, that means the lower the amount of water there is to a pound of cement. So if you see a 0.45, it means it's less than half a pound of water for every pound of cement. If it's a 0.60, that's a terrible mix. And in fact, it doesn't seem that dramatic. If you go, well, 0.45 or 0.60, what's the difference? Well, the permeability difference is probably 1,000-fold. So a 0.45 water cement ratio, for example, you can get what's called disconnecting capillaries in a 7-day cure. Whereas if you try to do that with a 0.60 water cement ratio, you'd have to cure for nearly a year to get the same type of permeability readings. How do you measure that? It's difficult to measure. Usually they'll use a gravimetric method to quantify it in a laboratory, which is kind of difficult to do, but it's accurate. And in fact, as we start segueing into flooring here, that's really what was my bottom line for beginning to evaluate test methods that have been used in the industry. And most of them do not agree with the gravimetric and have been misapplied. So that is basically my intent here, is to educate people on the proper method of moisture testing. Because irrespective of what's going on with the concrete, even though there's things that can potentially go wrong with the concrete, that has very little to do with the problems we're seeing today that cause millions and millions of dollars of damage every year that's totally avoidable. And this format is an excellent format, the IAQ Radio, of getting this information out to people.
Bob, let me ask one more question on that before we go into that topic on floor coverings in a little more detail. I used to work at a place called Pittsburgh Testing Laboratory. They were bought by PSI. And we sent guys out to construction sites all over the place. And I was in the environmental side, so I'm somewhat familiar with it. But they used to do a lot of what they called slump tests. What's a slump test for?
Slump test is to find out, is basically a test of the workability of the concrete.
Oh.
So the more basically take it out of a cone, and when the more it slumps or starts to shrink down, that's basically how they measure the slump. So
and is the workability, does that correlate to the amount of water or something else?
Generally, if it's just water that's in the mix, pretty much the aggregate size and shape can have some effect on it. For example, it's like comparing arrowheads with BBs. If you take arrowheads, you put them in a clump and you drop them, they just stay in a clump. You both BBs, and they'll spread out. So it's basically a balance of that, because you don't want all BBs, because all BBs you will not get what's called aggregate interlock, which is important for the strength of concrete for its long-term durability. So, but if you have an admixture, you can get away with a higher slump with less water. So there's certain admixtures that are called plasticizers. And they have some that are called super plasticizers, where that's where that self-desiccation concrete comes in, where they put these super plasticizers in, where you can get where the concrete's plastic enough to basically pour and place it and make it manageable with very little water in it.
Interesting. And one other, I think, kind of background question that goes back to the testing that I used to see. They would do compression testing, and they would put these cylinders of concrete on the I don't know what you call it. We used to call it the 2.1 because it could do like 2.1 million pounds per square inch of pressure. Yeah. The thing was unbelievable. Is that where you're getting that 3,000 pounds per PSI number that you were talking about earlier from that type of testing?
Yeah, the compression strength test. That's what it's called generally. I really dislike that test immensely, because that's being used as a judgment for concrete quality, which is one of the worst ways to judge the quality of concrete. Actually, one of the best ways to judge the quality of concrete is tensile value, but that's hardly ever used, and nobody's directed to use it. Because if you want to find out if concrete is of decent quality, the tensile value of the concrete should be at least 10% that of the compressive value. It means its ability. So if concrete's at 3,000 psi and the tensile value is 300 psi, it's really good concrete. Now, if it's 150 in a tensile pull, the concrete's terrible. It's brittle. It's not going to last. It's not going to be durable. But those numbers are never given to people.
Now, I'm used to seeing tensile on things like cable. Like we did the Brooklyn Bridge cables, and they basically pulled on them until they snapped. How would you do that with concrete?
Oh, they do. They have a pull test, and they'll use that for coating sometimes. And it's difficult to do with concrete because it's inconsistent. But there are methods, and one of the best ways, and correlates somewhat, is the ductility test, which is it's called a 3-point test, where they'll take a concrete beam, they'll put a center point, and then they press down, and they wait, and then when it snaps, that will correlate somewhat with the ductility will correlate with its cohesive values.
And with each type of construction pour, whether it be for a foundation, a footer, a bridge, whatever, are there different standards that concrete has to meet with respect to compression, tensile, etc.?
Yeah, and I'm glad you brought that up, because one of the things I'm involved with a case right now where the concrete was specified to ACI 318 and 301. But I said, that's an improper specification. And the attorney said, why? I said, because it's a floor. Floor is a non-structural item. It's supposed to conform with 302, not 301 or 318. And I'll see some warranties based on that as well. Warranties are based on structural concrete. Well, if it's non-structural concrete, what value is the warranty? Are not structural concrete.
I've got, we do a little construction up here at the lake, and basically we just have to kind of trust the concrete contractor to get this right. Is there something more that a homeowner or a builder could do to try and get this right before it goes to court and someone like you has to come in?
Oh boy. Yeah, I've been fighting that. If you can figure out a way to do that, it'd be great, because I've been fighting that for 30 years. And I run across the same thing over and over. I was involved with basically the first large court case I was involved with dealt with Hotel del Coronado in San Diego. Mm-hmm. And basically the engineers being sued by the owner because they said that the concrete cover over the reinforcing steel was improper. And they were all fighting over that and the chloride content of the concrete and everything else. So what I did is I looked back. The first thing I look at are the fundamentals. The specifications at the time and during the initial build of that structure had nothing whatsoever to do with the cited standards, because those standards did not exist at time of construction.
Okay.
But they were all arguing over something that was developed later and had nothing to do with that. And then I brought up the point where one of the things is the chloride content is too consistent. When I looked at the samples of the concrete when it was analyzed, and the chloride content was fairly consistent all the way through. That is not consistent with a seacoast structure. It should be higher towards the surface and get less and less as you get towards the reinforcing steel. So I gave the opinion that I believe that they used what's called calcium chloride during the initial pour of the concrete, because these were precast decks that were put into place where all the damage was occurring. And sure enough, that's what happened. We had it analyzed, and everybody assumed it was sodium chloride. It was not. Most of it was calcium chloride.
You know, this is fascinating to me. Bob, I love this conversation. But Cliff, I know you wanted to jump in. Maybe you had a follow-up or two.
Yeah, I wondered, Bob. Joe talked about working at the lab, and I've seen in the Pittsburgh area we have a lot of retaining walls that are made out of those concrete core samples that are taken, and I wondered how do they test those in the lab?
I don't know. Because I'm not involved with that type of construction.
Okay,
I'd have to look into it.
Gotcha.
I'd give an unqualified opinion for that.
Okay. So going back to the 3,000 pound test, does it break at 3,000? What happens?
That's the average. And the allowable variation of that is about 15%.
Okay. So it gets crushed, it breaks or whatever. Okay.
Yes.
Gotcha.
Yes.
Okay. Good.
And you don't want it to break until it gets beyond that 3,000 pounds per square inch, right?
That's preferred. Yeah. And again, I don't like that as a determination, because another one I was involved with was this petrographer brought me in over Texas A&M, and the concrete had conformed to their compressive values. They took cores and it worked, but they were having problems with the floors. And I looked at the floors, and the damage I saw with the efflorescence coming up through the tile, it was a beautiful green tile that was beginning to come apart from the alkalinity, which was basically causing it to separate in layers. So it looked like more like a buttermilk biscuit than it did the floor. I said, is there any place I could look at the concrete? And so anyway, they brought me underneath, and I looked at it, and one of my handy little tools is I use a coat hanger. Mm-hmm. So I took the coat hanger, I said, the concrete's the wrong color. And I started scratching. I was actually able to dig a hole in the concrete. I said, this concrete appears to be retempered. And they all looked at me like, what do you mean retempered? I said, what happens when concrete is being brought in and it's too hot, they'll add water to the concrete mix. And basically there's already cement formation occurring in the truck. So when you're mixing again while it's trying to form cement, that's called retempering, which weakens concrete.
It ruins it.
Weakens it mostly in its cohesive value rather than compressive value. So sure enough, we got hold of the mix tickets, and they said, well, what's the critical temperature? I said, well, since you were doing this in the summer, the critical temperature would be basically anything over 85 degrees. Every single truck that came in was 91 degrees and more.
How do they measure that, Bob?
Well, they're required, and that's the thing I like to do, they're required to have the concrete come in at a certain temperature. They don't always do that. Thankfully, they did. And basically, they take a temperature of the concrete as it comes out of the truck. And it was already at 91 degrees, 92, and even 93 degrees.
You put it like a thermometer in it, or you use a
yeah.
okay.
Yeah. Or you can use infrared. Infrared's the best way to do it, because then
That is the best.
you don't have to insert anything.
Okay. Fantastic. Hey, we've got a break and thank our sponsors. We're going to our halftime. We'll be back with the second half of our fascinating discussion on concrete. Sometimes the simplest topics, you end up with the most fascinating discussions. We'll have Bob Higgins back for the second half right after we thank our sponsors.
IAQ Radio Platinum sponsor is John Don Products, where restoration and abatement contractors shop. Visit them at jondon.com. That's JONDON.com. Gold sponsors are Particles Plus Engineers and Manufacturers of feature-rich particle counters and air quality monitoring instrumentation. Learn more at particlesplus.com. Count on us. Healthy Indoors Magazine, a free online digital magazine for industry professionals and consumers. Subscriptions available at healthyindoors.com. And AEML Laboratories, free FedEx shipping, great pricing, same-day results, and never a rush fee. Learn more at AEMLinc.com. Gray Wolf Sensing Solutions, who use advanced sensor software technology and embedded computers to provide superior environmental test instrumentation. Visit them at wolfsense.com. Association sponsors are the Indoor Air Quality Association, a multidisciplinary organization dedicated to promoting the exchange of indoor environmental information through education and research. Learn more at IAQA.org. And RIA, the Restoration Industry Association, the granddaddy of the restoration industry. Network with leaders. Learn more at restorationindustry.org.
CIRI, the Cleaning Industry Research Institute. See more deeply through science and research. Learn more at ciriscience.org. That's CIRI science.org. We are back with Bob Higgins for the second half. And Cliff, I'd like to turn it over to you because you and Bob spent some time together in Ireland, and I know you had put together some questions specific to your concern, your interests on this. So please take it away.
Okay, thanks, Joe. Well, Bob, we have probably 25 minutes left, about half the show, and I know that very close to your heart are issues that are going on in the flooring industry in regard to claims. And so we want to just give you this time to kind of educate us on what we should know and how we should know it. So if you could cover perhaps the quantity of claims annually, what causes the claims, how the claims could be prevented, how the claims are investigated. I'm just going to turn it over to you and take notes.
Okay. I was involved with a company where we did moisture mitigation. And as I started going out to these different projects, I started doing more and more analysis, taking it from what I've learned as a construction defect investigation. And I found that the majority of the problems I was coming across had nothing to do with what we were taught, which really was, and each one that I kept investigating, I thought, wow, at least 70% of the floors I'm looking at, the moisture is not coming from what I've been taught, because we were taught incorrectly, and most of the moisture testing is being done incorrectly, in that the interpretation is bad, and mostly it's unfortunately kind of dependent on the people who produce these materials. They don't understand concrete at all, so they don't even know what they're testing. So I found that as I started putting these things together, that my gosh, and talking to the different people in the industry, at the bare minimum, the amount of claims for the flooring industry go into several hundred millions of dollars a year, and maybe in soft dollars it exceeds $1 billion because of the damage caused by the floor, the reputation, cost of litigation, and ancillary damage. I found that at bare minimum, if we apply moisture testing correctly and we interpret it correctly, we can rid ourselves of a minimum of 90% of these issues, as it is not what we think it is. What we've been taught is that as you measure moisture in concrete, that's originating from the concrete. Nothing could be further from the truth. One of the simple ways I try to educate people is there's a couple of things that anybody can research. One is called slab sweating syndrome. That's where a slab of concrete will get soaking wet, even though it's not water coming from coming from underneath. It's water that's coming from the environment. It looks like somebody took a shower. And that's just caused by the environmental conditions. And the other one is if you do some research and look at wet basketball courts. Whether it's high school level, college level, or even the level of NBA, if you get the combination of warm, humid air and a cold surface, they can't dry the basketball courts long enough to have it safe enough to play a game on. So they've had to postpone, even cancel games, because they can't safely play on those courts without slipping. And that's all moisture from the air. That happens all the time in a construction environment where warm, damp moisture goes into cold concrete because water moves from warm to cold, high pressure to lower pressure. So, and the greater the difference between the air and the concrete, the more potential you have for accumulation of moisture, and it can occur over a period of time or rather quickly. So what I've had people start doing is after they've qualified the concrete, because most testing that I've seen that qualifies a concrete isn't bad. It can use some tweaking here and there, but that's not the big subject. Where this needs to be tested is immediately before and at time of installation of the floor, because that's when these elements are introduced. Because when you do the qualification testing, if humid air is introduced in the building, it's changed everything. And nobody has bothered to look at that. So I've worked with clients. There was one in particular in Florida. They have 6 offices, and they were experiencing monthly issues. They're now experiencing less than 1 a year. They have, in fact, the amount of problems they have when they think it's coming as a moisture problem, it's usually something else. But even then, they've cut their claims by more than 90%, and this happened over and over again. And I've dealt with a handful of clients, and to date we've saved them over $10 million in claims, and that barely scratches the surface.
Well, what kind of client are you talking about here, and how? And maybe you could give some specifics on how you got them to turn around this issue.
Okay, one of the things they would do is they would qualify the concrete, and they would use what's called a humidity probe. That's probably the worst way to qualify a piece of concrete, because a humidity probe only measures the airspace that's in concrete. It doesn't measure the concrete itself. Well, what measures the concrete itself is an impedance. Because I used to endorse calcium chloride tests, and I had for years. I no longer do that, because I found that now with the changes, which I don't want to get into, that have happened since the turn, as we've gone into the 2000s, there's other contributing factors that have made that test increasingly unreliable. But I found impedance testing to be very reliable. And where I had my aha moment was I was doing some research and found that Finland was testing some concrete bridge decks, and they were testing these different devices against the gravimetric. Gravimetric is the most accurate way of testing moisture, period. However, it is completely impractical for floors, because you can't. You can only sample small areas. It's destructive. There's handling issues. There's chain of custody issues. There's all kinds of things that make it too complicated. The moisture impedance, and fortunately, unfortunately, depending how you look at it, there's a real specific company. It's called Tremex. They make one that's actually designed for concrete, and it measures to 6%, which also coincides with the amount of moisture or amount of water that's in concrete when it's freshly placed. Starts at around 6%. So you can actually gauge its dryness as it drops in percentage. So I would go out and look at some of these jobs, especially lately, where they'll have a low calcium chloride reading. They'll also have a low relative humidity reading, but it's wet according to the impedance. Now, if concrete's alkaline, that happens all the time because it'll pull water in, but it's not measurable because salts, all salts, especially alkaline salts, will actually create increased resistance to evaporation. And that has not been taught in any of these schools or in inspection courses, which I think is a crime, because that is part and parcel to concrete. I mean, I actually talked to experts in the business that have been conducting these tests on floors for 30 years. They didn't even realize that water moved through concrete in a liquid form. They went under this mistaken belief that diffusion was the factor of how moisture moves through concrete. It doesn't move through concrete according to diffusion. Even in new concrete, that's difficult to quantify using diffusion. In fact, it doesn't happen because you get changes. In a laboratory, it's fine because you don't change anything. The temperature is the same, the humidity is the same, everything's the same. So you're dealing with basically a static condition. Once you have dynamics, you get into a kinetic condition. Diffusion no longer is appropriate because you get what's called I drew a blank.
No problem.
Hysteresis.
Hysteresis, okay.
Yeah, and basically hysteresis in concrete is highly unpredictable. They're still trying to understand it completely, and I don't think they ever will. I think they'll be able to get some grasp of ranges, but I don't think they'll ever really quantify that because there's too many different conditions, too many different types of aggregate. The cement doesn't have to be much different in alkaline content. For example, in about 2002, 2003, the EPA kicked in requirements for some of these concrete producers to recover their flue gases. When you recover the flue gas, you introduce more alkaline component to the cement. Now that doesn't show up very much in a pH test, but that's because the sodium hydroxide, which is the material that's recovered in the flue gas, is very, very buffered. Now buffering is important here because over a wide range of concentration, the pH doesn't change very much, but the activity level and the aggression of this material can increase dramatically, and sometimes by orders of magnitude, depending on what you put down on the floor.
Bob, let me see if I can understand and maybe summarize a little for myself and for listeners. So I think one of the contentions that you have is that at least in new construction and newer, let's say in the last 20 years, a lot of the moisture problems are coming from the environment, not from the air and the environment, not from below the concrete, and not water, water issues below the concrete moving up through the concrete. Is that somewhat accurate?
That's you put it really well. In fact, in my opinion, a lot less than 5% of the issues are coming from the concrete itself. So if we start controlling the environment, because we've had people go in with just fans and they've mitigated a problem with floor fans. And I was involved with this one project where I was doing consulting work for this large adhesive company, and they had 300,000 square feet of floor, and the moisture levels were high. Well, it was interesting is the higher they went up, and they were puzzled by it, as was their consultant who was doing the moisture test, that the second and third floors had higher moisture readings than the on-grade slab. So according to them, if the moisture is coming from the concrete, that shouldn't happen. I said, yeah, this is environmental. You're experiencing what's called a stack effect. Well, the guy running the test didn't even know what stack effect was. Why are you giving advice and doing moisture tests when you don't even know what causes this. I mean, that
Interesting.
happens all the time.
Let me see if I can summarize a second thing, and that is that I get the impression you feel the use of an impedance meter is a better way of measuring moisture than even, and what I've learned even just today is then better than even drilling down into the concrete, putting an RH meter down in there. That the meter seems to be a better way of measuring than the method they're using, I think, is considered the gold method, right? The Cadillac is to put the sleeve in, put your RH meter down in there, etc. Is that accurate?
Yes, and don't get me wrong, I love the humidity probe, because if you put a humidity probe in and your numbers are low, but the impedance numbers are high, it generally means you have some alkaline issues you need to deal with. So it gives you an virtue. Now, the impedance only measures the moisture. So if you're measuring the moisture condition of the concrete, the impedance is the only one that works properly.
Interesting.
It gives you the right information. Now, what I use is an infrared thermometer, I use a digital hygrometer, and the impedance. That's what you should test with the environment immediately before and during the installation. That's where we've been catching these influences as they begin to develop. Because sometimes when you're spreading an adhesive that has some moisture in it, the relative humidity in the room can climb and it can go into dynamic equilibrium. So this part of the floor where it was dry when they first started installing, it's fine, but where the relative humidity in the room began to climb, that's where they started having issues, because it wasn't drying properly. It was actually being pulled into the concrete. So by monitoring the projects, we've eliminated almost all of the problems that they experienced prior to that. And
with simple tools, a thermo hygrometer, RH meter, and laser thermometer. I mean, and so you're looking at the temperature of the surface of the concrete, the relative humidity of the air.
Yeah, and temperature of the air.
And the temperature of the air. Correct. And then you're using your impedance meter to verify the surface, the concrete is dry, and now you're looking at the environmental conditions around that.
Yes, because my first epiphany with this was in a high-tech project where we went into a room and we were talking. I had the hygrometer on. While we were talking, the relative humidity in the room was 52%, but as we kept talking, the relative humidity climbed to 78%. So what I had them do is I had them reenact what they did when they installed the floor and the adhesive. As they began to spread the adhesive in these rooms where there wasn't an active HVAC system, the relative humidity in the room went from 52 to 90%. I said, it's going to feel exactly the way you saw it before. And it did. So what we had to do is take it all up. We used an impedance meter where we blew air across it, dried the concrete back out to where the impedance meter was now below 3%. We had them reinstall the floor, but control the relative humidity in the room not to exceed 60%. They put the floor down, had no issues. And they repeated that throughout the project. And they were being told that they had to use an expensive moisture mitigation, which would have delayed the project by over a month, added almost $3 million to the project, and it was completely unnecessary.
Your timing on this is excellent. I'm going to Greenville, South Carolina next week, and I've got a school district I work with down there, and they're running into this exact issue with moisture. And it's an environmental issue, but the energy folks don't seem to want to believe that. So we're going to continue to push the energy folks to understand a little bit about psychrometrics, which you'd think they would know. But anyway, let me add another wrinkle to this, or another question for those of us that do inspection work where we've had water damage issues or whatever. There are differences in construction techniques from 50 years ago, from 30 years ago, from 20 years ago, from 10 years ago. We now generally will find new construction slabs will have a vapor barrier. They will have some kind of, coarse stone underneath them, better drainage, etc. Older construction, we can't guarantee that. I mean, we just don't know. And very old construction, that concrete may have been laid right on clay or something like that. Am I accurate in my understanding that some of these moisture issues in older construction could be from moisture coming from below, at least more often than they are in newer construction?
You're correct, because especially with the older vapor barriers they used to have what's called visqueen, and that was not a virgin plastic, and they were basically disassociated within 2 or 3 years of placement. So they were essentially gone. So you would get introduction of materials from underneath the concrete slab that would add additional hygroscopic elements to the concrete, and after a while, the moisture just starts rifling through. And one of the ones I do have, and I can share the photos with you later on, but there was an efflorescence in this one building over in El Centro, which is Central California. They said, well, we have this alkaline efflorescence. So I said, well, don't always assume efflorescence is alkaline. He said, well, yeah, it's coming from concrete. So I put down the pH strips, and the pH of the efflorescence was between 2 and 4. It was this efflorescence was, as we had it analyzed, was from, well, this was placed over some farming and agricultural areas, and basically the phosphates and everything else and the other materials they put in the soil as adjuvants worked their way through the concrete and actually was causing damage to the concrete with the alkaline efflorescence.
But now, the age of the construction would not, at least from what I'm understanding here today, would not change how you would evaluate the issue. You would still use your method you just talked about, an impedance meter, laser thermometer, thermo hygrometer, and do the same basic kind of evaluation. But I guess maybe you would add some things in older construction. Is that accurate, or?
Correct. Yeah, a newer concrete, those are fine, but an older concrete, particularly where they've already had a failure, always bring in a relative humidity probe. I cannot emphasize enough that you need both numbers to evaluate the condition of the concrete. As far as I'm concerned, in the evaluations I've done, I found those to be even more reliable than what's called a petrographic analysis. Because again, that's a spot test, very similar to gravimetric. It's useful, but only tells you what's going on right there. Whereas if you use a humidity probe, you can get an overall picture of what's going on with the concrete.
So the importance of a humidity probe increases with older projects than with the newer projects?
Correct.
Okay, fantastic. Cliff, let me turn it back to you. I know you still had a few more questions.
Let me add. It's indispensable. I would not recommend doing moisture testing on older concrete without using the humidity probes.
Fantastic. Excellent stuff, Bob. Cliff?
Well, Bob, let's go back to really the core issue and the core problem, which is this misinformation. And misinformation originates somewhere. And it's either the people don't know or they think they know, and what they know is incorrect. And then they repeat this. This information gets parroted. And I think what happens is in training organizations, a lot of times the people doing the training may not have the field experience, may not have the understanding. And what happens is they're parrots. They repeat what they've been told. And this goes on generation, and they lose generational memory, and you find yourself in a situation where there's a bunch of misinformation out there. And I suspect that's where we're at. I guess the question is, how do we fix it?
Good question. Well, through things like this, and what we're trying to do is we're putting together a group of people where we're going to try to educate people a little better. Mm-hmm. A good example, and I just read this in specifications in the master spec. It's alkalinity testing. Well, no, it's not alkalinity testing that you do on concrete. It's a pH test. people still, and I've talked to people in the concrete industry that do not know the difference between high pH and high alkalinity. They're completely different terms. You cannot use these interchangeably, but they do it all the time. You can actually have higher alkalinity and a lower pH.
How is that?
For example, if you have sodium hydroxide and there's, say, it's a 5% solution, but it's got a pH of 14. Now, the pH, now you test another piece of concrete and the pH is 10, but you have a 30% solution of sodium carbonate. That's a much higher alkalinity.
How do you find out what was installed? I mean, the specifications might be good, but if it's not installed to the specification, how do you know that?
Well, that's when you bring people like me in.
Okay.
That's what I did with Texas A&M, where I found that they did not, the concrete specified a certain way. Everything was done correctly, except they missed on the temperature of the concrete. They should have. Now, the people that supplied the concrete and also the person doing the inspection all got held liable for that, because there's, who's watching the hen house? Why did they should have turned away those loads of concrete. They should never have allowed that to be placed. But those concrete trucks sat there and waited. They were in a line. Somebody even had a photo of it. So when that was presented during the mediation, that it kind of ended right there.
Bob, again, going back to residential construction, these poor folks, they're hiring someone to put an addition on or build a garage or whatever the case may be, and they basically have to trust that their concrete guy knows what he's doing. Is there any other checks and balances that could be instituted for those that are doing this? I mean, I've actually thought about going into the concrete world because it's so hard to find good concrete people, but now I'm scared to death, actually. But I'm just wondering, how do we implement checks and balances? How does a consumer or a general contractor that's relying on his concrete guy, make sure that he's getting what he's paying for?
That is so difficult, because I have dealt with things such as ASTM, which when I went in bright-eyed and bushy-tailed and naive, thinking that we're doing this for the best interest of the industry. Seldom is that the case. So it begins from the very top. So by the time it's brought to the bottom, whatever's filtered out and whatever's brought is generally politically motivated or motivated by the almighty dollar. And unfortunately, that's the case here. We're given a lot of bad information. People assume so much. So what we're trying to do now, and that was actually one of the intents of going to Ireland, is to put together a team that would start putting this accurate information out. And it was really amazing to see these decades and decades of the different experiences and different exposures that these people had that all converged, that were in so much agreement with each other. It got me really excited. So I think we basically have to start over, because what we're doing right now is wrong. But that's a perfect example of insanity, is doing the same thing over and over and expecting a different result.
Yes, sir. Very well said.
It's not going to happen. So,
Cliff,
we have to change minds. We have to change the way these different industries sell their product.
And we hope we're being a part of that right now, Bob. Cliff, before we go, any final thoughts, questions?
Yeah, I think Bob's 100% right. I was there, and it was kind of like all these people had this epiphany, at the same time. But I think people learn differently, and I think a lot of times they have to physically see it. I don't know if it involves getting samples of concrete with these different conditions. And, I think if people see it and they test it, I think it'll register with them, Bob, versus maybe seeing a slide about it. And then I think I think people learn better when they have an opportunity to do it hands-on, and actually, make the diagnosis and learn from it.
I agree somewhat, except I don't think the emphasis should be on the concrete. I think the emphasis should be changed to the environment. We've ignored the environmental conditions because even suspect concrete will actually operate pretty well and sufficiently, because if you look prior to us doing all these moisture tests, the moisture, the rate of so-called moisture failures was much lower.
Mm-hmm. Is there a particular flooring that's less prone to it? Because it would seem that, if you had carpeting that, moisture vapor can get through that and release and can kind of go back and forth. It would seem that, if you put tile or marble or some of these other surfaces on top of it, that it would almost seem that you'd have less problems, because whatever, the moisture can't get into the concrete, because it would have to pass through ceramic tile or whatever in order to get into it.
Yeah, if any material that's got some permeability helps to keep it out of the critical nature, because it's just the critical nature of how some of these things are done. Like some of the repairs, some people will automatically go to an epoxy coating. Mm-hmm. Well, if you have what I call bad concrete, where they have ASR, the epoxy coating will make the problem worse.
What's ASR, Bob?
It's called alkali silica reaction.
Okay.
That affects about 18% of the concrete that's placed, no matter where it is.
Wow. And, we didn't even get a chance to go into all your knowledge on coatings and things of that nature, which I think we may have to do a follow-up show.
Absolutely. To do. We'll get them back.
Oh, you're a glutton for punishment, aren't you?
I like to learn, and I think that's a lot of our listeners feel the same way. They have a hunger for knowledge, and you've helped us provide a great deal of it today. Before we go, is there anything you'd like to add? Any final thoughts?
No, I love the format you have here, where we can get people educated, at least thinking, and contest me on these things. I want you to challenge what we're saying. Don't accept things sight unseen. That's the best advice I can give anybody. Please challenge anything that's stated, whether I say it, Cliff says it, Guru over somewhere else says it. Challenge them.
You got it. I just realized I missed a chat text question for you, Bob. They've run across cabinet suppliers that have placed new cabinets over poured concrete floors prematurely, causing mold growth beneath the cabinets. What basic testing method would you recommend to avoid moisture damage issues like these? I think I know what you're going to say, but let's go ahead and let you say it anyway.
Okay. Well, there's good news and bad news in that, because that reminds me of several projects I've come across. The bad news, you got mold. The good news, it's not coming from the concrete, because if the moisture is originating from the concrete, it's very alkaline. It will kill the mold. So you don't have an ongoing issue. You had an environmental issue that if they use the tools before they install the cabinets and put even fans or possibly a dehumidifier in there, it'll take care of the problem.
Gotcha. Fantastic. And also, if someone had tested that area prior to installing those cabinets, I think it would have helped as well.
Yeah, something as simple as a floor fan could have fixed that.
Mm-hmm. Wow. You mentioned floor fans a few times. Is that does that help even if you've got a high relative humidity environment, or do you have to do both, move the air and reduce the humidity?
There's a little complexity in that. However, if you get air moving across the concrete, you remove what's called the evaporative cooling effect. Because what happens, especially with evaporation, the coldest portion of the evaporation process is right at the surface interface between when the water is a liquid form and evaporates. So if you can remove that evaporative cooling effect, you make the evaporation much more
less likely, right?
Yeah, it makes it very effective.
More likely to evaporate.
More likely to evaporate. Yeah. Now, there's a trade-off there, because if you over dry it, what will happen is if you've got alkaline salts there, it'll start fighting you, and you think you're drying it out, and you're not drying it out. So there's other things you got to look at. But where he had the mold, that wasn't an issue.
Huh.
Now, if you have damage to the floor, now it's an issue, because now you got to worry about the alkalinity, because the alkalinity is generally what causes floor damage, not the moisture. Because I've taken these materials and stuck them under water and left them for a year, 2 years, nothing happened. But as soon as I add an alkaline component, they start falling apart.
Interesting. Bob Higgins, thank you so much for joining us today on IAQ Radio, plus an eye-opening interview on concrete issues and answers. Hopefully we'll get you back again soon.
Thank you for inviting me.
Our pleasure. And this is Radio Joe Hughes saying thanks to this week's guest, Mr. Bob Higgins, to my co-host, the Z-Man, Cliff Zlotnick, at the controls, John, you gotta have faith, and of course our growing group of loyal listeners. Next week I'll be in Greenville, South Carolina, but we will do a Flashback Friday show. And then 2 weeks from now, I've got Dr. Jill Christa joining us. We're going to talk a little bit more about mold health effects and how some of the MDs that specialize in that are treating patients, and then what their thoughts are on that particular issue. So we'll be back in a week from now with a flashback, 2 weeks from now with our next live broadcast.
For IAQ Radio, I'm Spike Reel saying thanks for listening.